Welcome to another podcast. In this episode, we're going to be taking a look at how to calculate limits, especially average velocities and instantaneous velocities from values in a table. What I have here is we are given a position function. So remember, S of t stands for the position as a function of time. So the position function here, and what I want to do is I want to estimate the velocity at time equal to 3. So this would be the instantaneous velocity at t equal to 3 seconds. So imagine that this is an object which is shot up into the air with an initial velocity, and eventually the object starts to come back down. And what I want to do is calculate the velocity of that object starting at t equal to 2 all the way through t equal to 3. So what I would like to do first is begin by looking at the average velocity over that time. And so remember, the average velocity is the slope of the secant line through the 2 points. So let's start by finding the slope of the secant line over the interval from 2 to 3. So remember that this would be the average velocity on the interval from 2 to 3. So the average velocity is defined in terms of the slope of the secant, and the slope of the secant line is the function value, which is the position function here. The function value at 3 minus the function value at 2 over 3 minus 2. And so taking the values out of the table, we've already calculated using this function. We've calculated the values of S of t at several values here. S of 3 is 156. And the position at time 2, which would be the height in this case, is 136. Let's just say feet per second is the units here. So 136 feet over 3 minus 2. That leads to a total of 20 feet per second. And notice that this number is positive. So this number is positive, which implies that the object is still rising. It's not falling yet. And you can clearly see here that its trajectory is going up. So this object is rising due to the positive velocity that we have here. So positive means rising, negative would mean falling. Now the slope of the line is also positive, and so we know from algebra that positive slopes imply the object is increasing from left to right, which it is here. Now, as we sort of get a little bit closer to the value, we can get a better feel for what the instantaneous velocity is by getting a point that's really, really close to 3. And so if I look at this point here, really, really close to 3, let's suppose that this is the point 2.999. And you can see from the table that the position values are getting ever so close to 156. So if I wanted to estimate the instantaneous velocity by using the secant line, so the secant line through these 2 points would be very, very close here. So the secant line through these 2 points would look like this. So if I wanted to estimate the velocity by using the secant line through those 2 points, then the way that I would do that is by calculating the average velocity on the interval from 2.999 to 3 and say that that's approximately the same as the instantaneous velocity v at 3. And so that's what we're going to use as our estimate for that. And so we calculate it the exact same way that we calculate the average velocity here. So using the secant once again, it would be S at 3 minus S at 2.999 over 3 minus 2.999. And so we have those values in the table. S at 3 is 156. S at 2.999 is almost 156. Divided by 0.000, no, just 2 zeros. 0.001. And when you do the division there, you'll get 4.016 feet per second. So you can see here that even though the slope is positive, it's starting to round off in terms of the velocity. It's starting to round off pretty quickly. Now, as we keep going with this problem, the idea here is that recall the limit as t approaches 3 of s of 3 minus s of t over 3 minus t. This is equal to the velocity at 3. And the closer t gets to 3, in this case t was 2.999, the closer we get to 3, the better this approximation is. And so what we can say right now is, using the approximation we have, that the velocity at 3 is approximately 4.016 feet per second. It turns out we're going to be able to calculate this exactly before too much longer. It turns out the exact answer here is 4 feet per second. And so our approximation using the secant line here is very close. So the average velocity over the last 0.001 seconds is approximately the same as the instantaneous velocity at 3 seconds. And so using information from a table, you can sort of quickly discern average velocities, instantaneous velocities, and at least get good approximations on instantaneous velocities at points. Remember, this is the slope, by the way. This instant velocity is the slope of the tangent line at the point t equal to 3. So if I was to look at the tangent line at this point, well, I guess I'll do that in red. The tangent line at the point 3 is something, well, it's definitely not that. It's something close to, let's see, at the point 3, something close to that. So you can see it's only slightly less elevated than is the slope of the line at 2.99. All right, thank you for watching.